Hi, my name is Mark Knutson from Keysight Technologies. I'm an EDA solution engineer working on high-fidelity system modeling applications, or digital twins, if you will. Today, I'd like to walk you through how easy it is to build a high-fidelity communication system with a pesky, tunable interferer in Keysight SystemVue. I'll walk you through setting up the data flow simulator, how to implement a full system, bits in, bits out, look at the EVM and spectral analysis as a result of our QPSK system up converter with an interferer poking its head in there in different parts of the spectrum. Just a quick word about SystemVue. It is a very powerful system design flow tool. You can directly link it to consume high frequency models from a variety of different sources shown on this slide. You can even take physical design tools like Keysight's ADS or EM analysis of antennas, boards, modules, ICs. You can bring that in and use that in SystemVue. You can also link to leading edge system measurement equipment, even leverage software that's used in Keysight's hardware, like VSA receivers, like the VSA 89600 software to demodulate simulated waveforms, or a combination of simulated and hardware measured waveforms. We're going to show you, I'll walk you through how you could build up a transceiver chain, transmitter, antenna, channel, and the antenna on the receive side, and the receiver architecture, and the baseband. And you can even scale that up with SystemVue. It has a phase array beamformer ability to do a scaling of very, very large systems with many, many different channel paths. You can start with a small parameterized behavioral models that say have gain, noise figure, power, compression versus frequency versus swept, SNR, EBF, or N0. And you can add in more real world effects as you need to. Today, we're going to look at an example that I find very useful and showing people the power of SystemVue and working with interferers. It's on our Knowledge Center website, and you can download everything from here. The link is right here. And there's actually 4 different test cases that are discussed in this example. We're going to look at test case 1, 2, and 4. Test case 3 is very similar to the first test case, so we'll just skip that one. But we're going to play around with different symbol rates and moving the interferer and the power of the interferer and interact with our QPSK information bandwidth signal and see what happens. So just a quick preview on test case 1, and I'll get right to the software and show you that in a second here. But we're going to basically open SystemVue. We're going to look at how it's kind of put together. We'll look at the equation 1, which I'll go through that in a second here, and defines how different variables are that govern how the simulation runs and the signal creation and where the interferer is, where the information signal is. We'll look at how that's set up. We'll walk through the schematic, in this case SCH1, schematic 1, and walk through how that's put together, how you'd run a quick simulation and get results quickly, look at the spectrum and get EVM results. SystemVue has, and I'll show you this, has a digital demod, like a dynamic sync, it's called, digital demod block, and it will basically give you live constellation results, EVM, spectrum, different other impairments you can measure with that. In this case, for test case 1, you're going to see that it has very clean signal. So let's go right to it. Before we go to test case 2, let's see that in SystemVue. So if I bring up SystemVue here, this is the example that's provided that I'm going to go through. It's already set up for test case 1, but let's before we do that, let's look at the equations and how it's kind of set up. So the equation 1 block is set up to have basically a symbol rate, 48 megasamples per second, bits per symbol, symbols per samples per symbol, in this case 16. Oversampling is related to that. The sampling rate is computed based upon the samples per symbol times the symbol rate, and the bit rate is computed as well. So those variables will be used throughout the schematic and to govern how the simulations run. If I look at schematic 1, which is right here in the tree, schematic 1, if I zoom in on first of all, we encounter a bit source. So this source is set up, and it's actually using the bit rate which was defined in our equation 1. And so it's set up untimed because we're going to add timing information later on in this data flow simulation. But off the top, it's just generating the bits, as we've governed here based upon, pseudo-random bits. By the way, the sample rate variable in the bitrate source is set to a sample underscore rate. That is tied to the data flow controller. That is a reserved variable, sample underscore rate. If I go to the data flow DF1 controller, that is sample underscore rate is tied to what is set here. So it's getting it from the equation bitrate. But that's what that sample underscore rate means. It's a reserved variable. So this is how we set up the data flow simulation. And we've got some random bits coming out. We can do mapping. In this case, we apply QPSK mapping to it. We have our root raised cosine filters, low pass filter, root raised cosine filters here. And just show you how those are set up. So again, we're using the variables that we defined in equation 1. We've got some roll-off, and we have our oversampling set based upon the equation. I forgot to mention on the data flow controller, so we set up there's also a tab for options. That's the general tab that I looked at before. On the options tab, you can say display data flow information. If I make this really big, and I run the simulation really quick, by setting in data flow 1, options block by checking display data flow information, that allows me to hover over different nodes in the system and see, like in this case, the sample rate 768 megahertz, mega samples per second, and the carrier frequency FC is 110 megahertz coming out of this upconverter before we go into the IQ modulator before we go into the upconverting mixer. One more thing to mention is if you do view and you check workspace variables, that automatically computes automatically evaluates these different variables bit rate that we defined here. It gives you the values that they evaluate to. So that's two different ways you can check your work. You can see it on the nodes. You can see it evaluated here. Now, so we've got a random bit source. We've gone through a root raised cosine filter pair, a QPSK mapping, upconverting IQ modulator, an IQ modulator, and now we're going to go through the upconverting mixer, set for sideband upper. We've got 110 megahertz going in, and out of the IQ modulator, we have an LO at 9.89 gigahertz, and in upconverting, that'll put this about 10 gigahertz coming out. And now we're going to add an interferer. So we have an interferer right now. It's set to 10.52 gigahertz. This has the tune variable set. The other thing I could do is I could type the function tune, TUNE parentheses around like symbol rate, tune TUNE parentheses, open parentheses to the left of the 48 megahertz, and then a close parentheses. That's the same thing as heading the tune bar here. But in this case, I'm tuning the frequency of the interferer. 03 is the oscillator. And then if I continue on, there's a add ENV. So what I'm doing is it's very easy to add signals. In this case, the interferer with our information QPSK signal. We're adding those together, and then we're moving the characterization frequency FC to the middle of those two signals. And so that's what I have the SC change. I've set that. I want the FC to be set to 10 gigahertz. So it's going to add the two together and reset the characterization frequency to 10 gigahertz. Then there's a bunch of sinks in the data flows. There's a spectrum analyzer, S1. There's an EVM block, and there's also that digital mod D1 ENV block that I mentioned. Both of these are going to actually give EVM, but digital DMOD is going to do more. If you push, basically what these are mini receivers, because you're setting up to demodulate a QPSK signal with a roll-off and the comparable receive side of the root raised cosine filtering, and we're doing the same thing in the digital DMOD block. The digital DMOD, as you'll see here in a sec, will give you a lot more. It'll give you the constellation, along with the EVM and the spectrum. but very similar setup there. So the result after running these is, let's do that. Let's run test case 1. What we see is very clean constellation, a very low EVM, 0.8 point something like that %, and that's coming. I can stop this. That dynamic display is coming again from the digital DMOD ENV block. So, and then what we see in the spectrum that was captured here, the output is coming into this S1 power plot. And so we see the leakage of the LO, which was at 10.89 gigahertz. We see our interferer is not really interfering right now, but it's out here at 10.152 gigahertz, way out here. You can set it via a tune bar right here, or in this case, I'm setting it with a hard value. This is when you have view tune turned on. So that's what I see there. That is test case 1. And we're also measuring the EVM coming out of the EVM block. And again, it matches what the digital DMOD block is, about 0.8%. So really clean signal. Let's do test case 2. Test case 2 is we're going to increase the symbol rate by a tenfold. Keep everything basically the same and see what happens. So to do that, one great feature of SystemVue, if we want to see appreciable change when you make a change in like the spectrum, is you can checkpoint graphs. So I'm going to select, it's context dependent, I'm going to select this S1 power plot, and I'm going to choose this little icon here called checkpoint, or you can hit the C key, and that's going to basically save in memory what test case 1 looked like. Now, what I'm going to do for test case 2 is, as I mentioned, I'm going to basically go in here and I'm going to increase the symbol rate by a factor of 10. So it's 480. I can right click on here and say run equation, and you'll see everything got updated. So if I can see this here, 1 second, we've got, so I've got 480 megahertz symbol rate, and then the sampling rate is now 7.68 gigahertz. Big difference. So what's going to happen? What's your thoughts on what's going to happen? Let's find out. I'm keeping everything else the same. I'm keeping the interferer still at 10.52, keeping the power the same. All I did was change the symbol rate. So if I run this, now we see some really bad constellation. We see 38 something % EVM, pretty bad. And I can stop this and let's see what happens. So the darker red is test case 1 at the lower symbol rate. By increasing the symbol rate by a factor of 10, now we basically increased our whole signal. So now the 10.152, which is in here, is in our information bandwidth. That's why it's so bad. So basically by spreading the signal, by increasing the symbol rate, that's what happens. So we get that case. Now let's look at the test case 4. So what we're going to do on test case 4 is we're going to go back to our 48 mega samples per second symbol rate. We're going symbols per second rate. We're going to that'll put the sampling rate back to 768. This time we're going to change where the interferer is with the original test case 1 condition, but we're going to change the frequency where the interferer is and the power. So let's do that. Let's go back to 48 mega symbols per second, and we're going to change this to, I believe, 10.028 gigahertz. And we're going to increase the power to 0 dBm. This is also reflected on these tune bars that are governing the interferer signal here. Now this is a CW signal, but this could be, there's a lot of other great examples you can play with. These could be totally different modulated signals or susceptibility signals or different things that you're looking at, coexistence signals that you need to test. SystemVue can add them together pretty quickly and easily. And so let's see what happens if we change it to 10.028 frequency of the interfere and the higher power. Yeah, it's looking pretty bad. So why is that? Let's see what happened. So you can see the checkpoint still on there, and if I turn the checkpointing off, which is clicking on this or hitting the C key, now we see that our interfere that we moved to 10.28 is in the information bandwidth. So it's just wanted to walk through a really quick and easy way in SystemVue to play with an interfere signal. There's so much more you can do with this and add in more complicated scenarios, frequency hopping, lots of different things. But just it's a great sandbox a didactic sandbox to find problems in your system and quickly and easily mitigate them and correct them and update your design. Hope you enjoyed this. Have a great one.